So I'm the last obstacle between you and your next coffee. I will try to make it short. I'm going to introduce you the package kmlShape. I'm Christophe Nolini. So I'm going to So I'm going to speak about trajectory. Trajectory is repeated measurement. So, for example, in this case, we measure the aggressivity score every year between age of 6 and 15. So it gives us a trajectory. And when we have many trajectories, we can't say anything about the evolution of aggressivity. So we need to cluster the trajectory to find some pattern and to put people who have similar trajectory in the same cluster. This is something very classical. What I'm going to do today is to work on shape. So on this example, we have four people, and many classical clustering algorithms will just put together the blue and the red. The classical algorithm just put together the people who have similar shape. And so here, the algorithm will say the blue and the red have similar shape, and the light blue and the orange have similar shape. So the algorithm will find two clusters, and sorry for my English, the mean trajectory of each cluster are the one drawn down. But in some specific case, we don't want this to happen. In some specific case, for example, if this is some degree of illness, we do not care that some people are ill in January, some others are ill in June. That's not really important. What is very important is that some people were slightly ill and some people were definitely very ill. So we would prefer to put the people slightly ill in one cluster, regardless they are ill in June or in January, and some other people very ill in another cluster. So this is, and then this will be the mean trajectory of each cluster. This is what kmlShape is about. So a classical algorithm to cluster data is k-means. K-means use distances and the mean of each cluster. kmlShape is based on a shaped k-means. So to have a shaped k-means, we first define a shaped distance, and then we define a shape mean. What is a shape distance? A shape distance is a distance that will be small if two individuals have trajectories that are closed according to their shape and no longer according to the classical distance. So for example, these two trajectories, according to the Euclidean distance, this is the computation of Euclidean distance. Then you take every segment, you put it square, and you know it. And this is the Fréchet distance. The Fréchet distance is for each point the minimum distance between the point and the other curve. But you don't have to be vertical. You can be in any direction. And then you take the longest segment that's separate the two trajectories. Let's take an example. We want to cluster the three curves, and we want to know if I1 is closest from A or from B. If you use Euclidean distance, we can compute it. It's quite easy. The I1 is far away from A, and I1 is close to B. So they will be put in the same cluster. If you use Fréchet distance, the I1 will be found to be close to the curve A and will be far from the curve B. And so, using Fréchet distance, I1 will be put in the same cluster than A. So we found a distance that respects the shape of the data. Now we need a mean that respects the shape of the data. Why? Because if we manage, using the Fréchet distance, to say that all these curves are in the same cluster, if we compute the classical mean, here here is what we're going to get. So this is no longer, we no longer have the shape of the data. So we need this is what we need to represent the shape. So we need a Frechet mean. It's quite easy with two curves. You just need to draw, in fact, the distance between the two curves, and then from each segment we take the center, and if we take the center of each segment, it draws a new curve, and we can take this curve as the Frechet mean between the two curves. So this is easy for two curves. We don't have two curves in a cluster, we have n, and we can have a Frechet mean between n curves, but then the complexity is t power n, which is probably, if you have 100 subjects and 10 measurements, it is something like the length of the universe. So it's too much. I don't have that time. So in order to find a shortest Frechet mean, we play tennis, and we make some kind of tennis tournament. So all the curves are an entry of the tennis tournament, and then we take two and we compute the Frechet distance, the Frechet mean between these two. We take two other, we compute the Frechet distance, the Frechet mean between these two, and then we take the two Frechet distance, the two Frechet mean that we get, and we compute the Frechet mean and so on. And at the very end, we get a final Frechet mean, which is not the real one, but as you will see, this is not far away.
So that you start random at the beginning?
Yes.
Okay.
You might suspense. Yes, it works. So let's have a look. So I just start with some artificial data in which there is obviously two groups, high one and low one, and if we use classical classification algorithm, we will find two groups, the red one and the blue one. And using kmlShape, takes time to converge, but quite fast. We found two groups. The first one is the red one with the high disease, and the second one is the green one with the low disease. So it works. It works, but it's very, very time consuming, and I show you an example with 100 trajectory. If you get 1,000, it will not work at all. So we have many ideas to reduce the complexity of the algorithm. The first one, we use Frechet distance. This is for sure, this is the base of the work. But we notice that if the trajectory are very similar, Frechet or Euclid gives almost the same result. So on one side, I draw the Frechet mean, and on the other side, I draw the Euclidean mean. I never remember which one is which one. So the difference is very subtle. So one idea is, if we get many, many trajectories, instead of computing the Frechet mean, we will first compute some resumate data using the classical K-means algorithm to make some kind of election. So in every department, we will elect a senator. So instead of computing the Frechet mean, we will first make some election with, for example, 15 clusters. If we decide to, if we have enough cluster, every single trajectory will be very close to one cluster. So it will be really be representative of the population. And then we make the Frechet means on the 16 cluster. Let's try again with 604,000 people. The Frechet mean, it will never end, whereas we make an election with only 16 senators, and we compute the Frechet mean. So this simplifies really the number of individuals without changing the final result. We can also reduce the number of measurements. So this is a curve with a trajectory with 100 measurements. and we can use some kind of algorithm that will extract some point to keep the same shape for the trajectory with less point. So this is with 20 point, this is with 10 point and a bad algorithm, and this is with 10 point and a better algorithm. We can see that it did not change really the shape of the trajectory. Of course, it changed the shape, but we're going to make some mean, and we are going to make a lot of approximation. So this first approximation does not really matter. This is called Pucker-Douglas algorithm, who simplify the number of points in a trajectory. So overall, we have a data set with n individual and t measurements. On this data set, we want, if the n is too big, we will not be able to run kmlShape, so we will first run a classical kmeans to elect some senator. With n0 senator and then t measurement, if t is too big, then we will also simplify the number of trajectory, and we will get n0 senator and t0 measurement. Note that if n is not too big, then you can go straight and run kmlShape. And then we run kmlShape, who give us the final partition and the average trajectory of each cluster. Let's try it. I'm crazy. My very first user conference, I make some example like that, and it did not work at all, so I crashed in front of many people, and in addition, it was not even on the screen. So I was playing with my computer during 5 minutes, but I still like it, so let's see if I improve myself. I'm cheating. As you can see now, I put some set seeds. Okay, this one we already see it. So I will make some bigger data set. I will not try kmlShape on this big data set because it will take a long time. I will reduce the number of trajectory, and here is with 32 trajectory and only 10 measurement point. Yes. No, here is 10. The previous one with many measurement points. This is with 10 measurement points. So we try kmlShape. It's very fast because the data are small, and we see that the shape is a bit with angular. So we decide to add more point. So this is senator with a bit more point, and then we run kmlShape, and again it's very fast, and then it's more smooth. So it works. Application, because when we find something very new, we definitely need to find a sexy example to present it. Otherwise, it seems useless to the community. So this is the trajectory of Alzheimer's disease during 2 years, every 6 months, we register the score called MMS about Alzheimer's disease. And so the trouble with Alzheimer's disease is we don't know when it starts. People came, and we know that the illness is not at some specific age, and when someone came to the hospital, we don't know if it starts 6 months before or 2 years before, and so we don't have a starting point. So we collect data, and then we cluster them, and we find that, which for statistician is almost the worst. There is almost nothing to say. You say, okay, you arrive at a good level, and in 1 year you will be a lower level. Well, it's 120 euros for the consultation, thanks. There is nothing very relevant. So we try using the shape, and we found that, which is some kind of major advance in the Alzheimer's disease. What we found there is a group which we call rapid decline, They arrive, everything seems to be fine, and maybe in 1 year they will have lost almost all their potential, which is which opens now some new way of making research. We're going to take these specific groups and we're going to check if there is some parameter, if they have some habit, or if they smoke too much, or if they don't smoke at all, or find any characteristic of these groups.
You can go on since you have the last one.
Anyway, okay. But anyway, I was just this is for the
Yeah, this is for the question.
this is for the question. So thanks. Before question and before everyone go to take the coffee, I just make a small advertising with my team. I'm also trying to rewrite the interface of R, and the project is called R++. So my commercial tell me, hey, you're going there, you have to make some advertising. So that was just one word. Question? Yes.
Yes, please.
Fascinating talk. From what I see, there is nothing that would stop me using this method on closed curve. For example, cell inference. There is nothing which says it must be a function. Because that distance can be done on closed curves. Oh, no, rotation and so on.
Yes, I think you can.
But there's a problem that it could be a rotated problem. The rotation would not be generalized.
I'm not sure what closed curve is.
Closed curve is a cell outside of a cell. A cell from
Okay, I understand. I never try, so this is a very interesting question. So far, I just try with trajectory in which there is a timeline, but I know that the Frechet distance works on curves and not only on trajectory. So Frechet distance, you can draw two curves and then you compute the Frechet distance. It works perfectly. I don't see anything that will prevent it us to.
It will not be a rotation invariant, for example. This would be a problem.
Okay.
Yes.
First, a request. We love your code too. Could you please upload this to get the slides for us to test?
Oh, yes. Okay, but my code, I did not sell it, but when I'm trying to make a package, I try to make it very user-friendly. So the package, all these code are in the example of package KML.
Okay. And my question, how did you decide to use 16 clusters for reduction and 10 data points for reduction? Okay. So I rolled the dice.
No. You try with 16, and it gives you some result. And then you try with 32, you get some result. And you try with 64, and you get some result. And you realize that it's the same. It's the same than you can use 64 or 50 or 32. It's the same. So after some points, you just decide that it's enough. Now, if your trajectory are something like that, and they have very, very complex shape, then I guess that 64 will not be enough. The claim is 64, if I draw 64 trajectory, you cannot even imagine a trajectory that will not be close to one of my 64. If now you have some very, very complex trajectory, this claim might not be true. So if you have very different kind of shape in your first data set, you might need more than 64 senator.
Thank you, very interesting. What's the source of the Alzheimer data that you analyze?
Sorry?
The Alzheimer data that you analyze.
Ictus. I'm working with Sandrine Andrieux, who is a medical doctor leading a team that work on Alzheimer's disease.
Okay. Yes.
What do you do when your data is noisy?
So before the Douglas-Pucker algorithm, thank you for making me showing my back slide. So when we have noisy data, this is what we'll get as Douglas-Pucker algorithm. So before doing that, we soften the curve using one of the many methods to get some softer curve, and then you can use the Douglas algorithm. Everything, I'm a pure statistician, everything in what I show is wrong. There is approximation everywhere, there is random, that's crazy. I mean, when I show that to mathematicians, they just want to shoot me. But it works, because what we do when we compute a mean, we take the average and we cut everything that is too high, everything that is too low. So this is what we're doing here. So on this particular subject, if I do that, he will maybe be offended. But I don't care about this particular subject. I will shuffle him, I will merge him with 1,000 other subjects. So this is wrong, yes. This is an approximation. But it works, because we want the mean at the very end.
Yeah.
I don't take the maximum distance between two shapes. I take the Frechet distance between two shapes. No, to compute the Frechet distance, you take the first curve, you take the second curve, and you move step by step, trying to find some path, and then you pick the biggest path between the length of the biggest segment. This defines the Frechet distance. You can do both. Frechet distance, when Frechet wrote his article in 2 centuries ago, he defined the maximum or the sum, and you can do sum square, you can do whatever you want. This had more, yeah, you can in the package I define 2 methods, maximum or sum. So you can use both. Yes. In my package, the curves are not continuous, but everything is defined basically on a continuous curve. Frechet defined his first distance on discrete curve, but after that, many mathematicians make the same on continuous curve, and you can also make the mean Frechet distance as I define in a continuous curve. Good luck for the calculation. But that's very interesting.
Okay. Any other question? Okay. No. Thank you again to Christoph Giannolini.